We're going to look at factorization. Perhaps initially look at a fairly simple factorization on this side, and then maybe do completing the square on this side. So always have the view that you should always aim to try and factorize any quadratic simply. So by that we mean that if you take something like x squared plus 4x plus 4 and factorize that, try to remember one or two things. You can factorize this in the normal way, but if you notice that if half of this value squared is equal to that value, that's an indication that it's a perfect square. Let's pretend we don't notice that and just proceed as we normally do. We normally write our two brackets and we say we can put an x there and an x there. This tells us that the signs are the same, so the signs are the same. But not only that, it tells us that the signs are given by the term in x. So just visually we've kind of more or less done 2/3 of the problem, and all that remains is to put in the factors of 4 here that will yield the 4. Well, the factors of 4 are 4 and 1 and 2 and 2. Clearly 4 and 1 cannot combine in this situation to give you a 4. They will only combine to give you a 5 in fact, and so it has to be 2 and 2. And so you notice, without perhaps recognizing it, that this quadratic expression was in fact a perfect square. Had you noticed that from the start, that half of this value squared is equal to that value, tells you that it's a perfect square. If I make another one up, can you see that half of this value squared is equal to that? So this is also a perfect square. But this time we can simply put half of that value and recognize it's this. This all comes down to the points that I've been making about having a clear view of expressions like that. Notice that in a perfect square, that has got to always be plus. Even if half of this is equal to that, but you've got a minus sign there, that is definitely not a perfect square. Well, let's now look at a situation where we want to factorize something by completing the square. If you try to factorize that, you will see that it does not factorize easily. You might say, well, I've got the factors of 2 and 1, and here the factors of 9 and 9 and 1, and 3 and 3. And if you try to factorize this by putting a 2x there and an x there, this tells us that the signs are different. So the signs are different. So we cannot at this point put plus plus or minus minus, we have to wait. And because you've got these factors, no matter how hard you try, there's no way that you can generate that 6 there. 2 times 9 and 1 times 1, 18 and 1 will never be able to generate a 6. 2 and 9, 2 times 1, 9 times 1, so 9 and 2 will never be able to generate a 6. So this is out. Clearly 2 times 3 is 6, 1 times 3 is 3. Again, that can't generate a 6. And whichever way you do it, you realize that this expression cannot be factorized easily. So really, you would understand that pretty quickly. When you come to complete the square, you'll see you're going to make use of the fact to your benefit that half of this number squared is equal to that. We can make use of that to force something to be a perfect square, and that's why it's called completing the square. Before you complete the square, you must always make the coefficient of x squared to be 1. You make the coefficient of x squared to be 1. So in this case, we have to take the 2 outside. We have no choice but to do that. And when you factorize the 2 here, you end up with that. What I'm going to do at this stage is focus on this part of the expression. And I can force this to be a perfect square simply by adding half of this number squared. So if I just simply do this, and I add half of that squared, I will know that this is a perfect square. But obviously I can't just simply add this number. By adding it, I've just changed the expression. So the trick we use, we add it, and at the same time we take it away. So this part up to here, you have to agree, is basically the same as that. It's as if this doesn't exist and all you have is x squared plus 3x. Of course, we still have that minus 9 upon 2, which we haven't forgotten about. We cannot get rid of that. But what we've done now, this part now is a perfect square because of our use of the fact that half of that squared is equal to that number. Half of this squared is equal to that number. So I can now write this as, x plus 3 upon 2 all squared. And what I have left here is minus 9 upon 4 minus 9 upon 2. And all I do our usual trick of making the denominator of those two the same. So can you see that this is minus 9 minus 18? So we can write this as now 2 into x plus 3 upon 2 squared minus 27 upon 4. Now when we've got it down to that stage, we can see that we can force this to look like something squared minus something squared. Although that doesn't look like something squared, we know our trick. We can always force it to be something squared by square rooting and squaring. So when you square root something and square, it's as if you haven't done anything to it. So now we really have made it look like the difference of two squares. That squared minus that squared. So it reminds us of the other important relationship that a squared minus b squared is a minus b, a plus b. And so what you can do here now is write this as 2 into a minus b I can take the square root of 4 and call it 2. So this is like root of 27 divided by 2, x plus 3 upon 2 plus root of 27 divided by 2. So that technique is one way of completing the square. It's not the only technique, and there are other ways, but this is one way, and this is an expression, remember, not an equation. So you can't take things over to the other side, and that's the answer in this case.